so far we were dealing with, we started by saying that in the neighborhood of the equilibrium points, the equation would be of this form. But then we had reduced it to the form x dot is equal to a x and went ahead with that solution. Why? What was the logic? So far all the solutions that we have obtained were of this form. So why not of this? What was the logic? That we first tried to understand what happens in the neighborhood of the equilibrium points, and we said that the effect of this is basically to decide the location of the equilibrium point. This would be 0. So, the location of the equilibrium point will actually be given by this term B u. Can you see that? So, if this is 0, x, the solution would depend on the B u vector. So, if this is not there, it is the origin. If it is there, then it will be something other than the origin. So, the effect of the external forcing, the external term, would essentially be to decide the location of the equilibrium point, and then we said that okay, let us first put that out of our consideration. First, let us try to understand what happens in the neighborhood of the equilibrium point. So, we considered this, and then we have obtained, we have understood what happens if this x is a 2-dimensional vector, what is if the x is a 3-dimensional vector and all that. But now, let us take this into consideration. So, what will be the effect of this? Obviously, the effect will be nothing but a non-origin equilibrium point, that is all. So, if you have a, let us take an example circuit. For example, if you have a circuit something like this, a battery here connected with the switch to a RL circuit. So, if this switch is closed, the applied voltage will be what? It was earlier 0, at this point it will rise to some value and then it would be like this, fine. So, the applied voltage on this RL block will be initially 0 and then at some point it will be applied. So, this is the applied voltage V. In that case, how would you obtain the solution? Firstly, this problem is trivial and you have all learned how to obtain the solution in your math classes. So, but here we will do it in a slightly different way to obtain a bit of conceptual clarity the way we wanted to do in this particular course. So, let us first do it the way you have already learned. So, what will you do? You will first write down the differential equation. The differential equation is V is equal to the Kirchhoff's voltage law plus fine, that is the Kirchhoff's voltage law. So, you have d I dt is equal to V by L fine. So, we need to obtain the solution of this. This is a one-dimensional first order equation. So, it is very easy to obtain the solution of this. Can we all obtain? The way you have learnt to solve it is by separating the variables. If you separate the variables, dt comes in one side and I and di comes to the other side. So, you will write dt is equal to L becomes common L bi by V minus Ri, right. See, we started from here. So, you have dt in one side L and di by V minus Ri, right. and then you would integrate this. The integration would mean it would be t plus an arbitrary constant k. This will be integral of this ln of fine. Now you have to obtain the or we can write this in the other side, v minus r I is equal to exponential. So, some constant times exponential minus L by R t, sorry, I will write once again, v minus r I is equal to sum a e to the power minus, okay. This a then has to be obtained from the initial condition. Suppose the initial current is 0, which is natural. So, in that case how will you obtain a? What is a? T is 0. So, this term becomes 1, this is 0. So, you have a is, this is 0, this is 1, this is 0 is V. So, the solution becomes I is equal to V minus R I or is it visible? Yes, 1 minus, okay, that becomes the solution. Now, this is the standard way of solving it. Given an equation like this is how you have obtained, you have learnt how to solve it in your math courses, right. Separate the variables, integrate them and then write. In this course, we will take a slightly different route only for the sake of conceptual clarity. We will say that what has happened, here we have an equilibrium point somewhere else, my starting point is somewhere else. We know how to solve the equation if the equilibrium point is the origin. So, we can do that easily by introducing a new variable, say x, which is, say x is where should I move it? Where is the equilibrium point now? Where is the equilibrium point now? V by R. So, we will make the coordinate transformation as I minus V by R. So, for x, that is the equilibrium point. If this is the new variable x, in terms of that, how does the original equation look? Original equation was this. So, this gives dx dt is equal to straight. So, you have the equation to be written as dx dt is equal to v by L minus r by L I. R by L I is x plus, right. You can see that v by L minus r by L x minus consists of v by L consists of is equal to minus. So, the equation is simply a x dot is equal to something times x. So, dx dt is this. Its solution you already know. What is the solution? X of t will be x naught e to the power Okay. What is your x naught? X naught, see, if the initial current is 0, the x naught is the initial deviation from the final equilibrium point. How much is that? What is x naught then? If I at 0 is equal to 0, then x naught is, yes, x naught is minus v by r. Fine. So, that is the initial deviation. So, the solution immediately comes out to be x of t is minus v by r e to the power minus r by L t. Now, you substitute what is x? X was I minus v by r. So, I of t becomes v by r 1 minus e to the power. That is the solution. We had already obtained it, but now we did it a slightly different route. What is the advantage of this route? No algebraic advantage really. It is only the conceptual advantage that what we do is, we know that what has happened is essentially that the equilibrium point is somewhere else. So, my initial condition is here. So, I will do everything around the equilibrium point. So, we simply redefine the coordinate and obtain the solution, and then this immediately comes out. The advantage will not be immediately apparent from this very simple case, but it will be apparent when we consider, for example, a square wave as the input. What happens then? If you try to obtain the solution algebraically, it will be unnecessarily complicated. In terms of concept, what is happening is that the equilibrium point is moving from here to here and back. Equilibrium point is oscillating between two different positions. So long as it is here, it will try to approach it. Before it reaches, this fellow comes here. So, it will again try to approach it, and so on and so forth. So, if you look at it from the point of view of the solution around the equilibrium point, that also will become rather simple. But at this stage, it will be necessary for us to introduce the question of how fast or how slow it goes there. For example, what will be the solution like? This solution, how will be the graph like? At t is equal to 0, it will be 0, 1 minus 1, right, 0 has to be 0, and when t is equal to infinity, v by r. So, it rises like this. Natural question is, how fast does it rise? How fast does it rise? So, here is t, here is I, here is v by r. So, it could be like this, it could be like that. So, how fast does it rise? So, the standard way of answering that question is to write this in the form, solution is written in the form I is equal to v by r 1 minus e to the power minus t by tau, where in this case tau is equal to, okay. So, t by tau, yes. So, L by r, and this term tau is the time constant. Now, you probably most of you have done this, right, or is it all time constant, the simple concept of time constant, you have all done. Just to recall, what is happening is that, what does this say? Tau, okay, consider the solution, the slope of the solution exactly at this point. So, what is the slope of the solution? d I dt is from here, just do that, this goes off, it is v by r, then in the denominator there will be tau, and you have e to the power minus t by tau. At t is equal to 0, this goes off, it is only this, it is only this much. So, at t is equal to 0, slope is v by r tau. So, you have tau di dt is equal to, this means that if this one were to continue, then this means that this slope times the time tau gives v by r. So, after a time tau it will reach the v by r. So, this time is tau. So, tau essentially says that if the initial slope continued, then after a lapse of a time tau it will reach the final value, but it actually does not, it actually goes like this. But what does it say? If the tau is small, then obviously it rises fast, if the tau is large, it rises slow. So, how fast or how slow this rise is given by the time constant tau. Smaller the time constant, the faster the rise, the larger the time constant, the slower the rise. Good. So, that is the idea of the time constant. There is some books in which it will be given in a slightly different way. They would say that okay, if after a time tau, where does this reach? Yes, if you just substitute here, substitute tau here, you will get, do that. No, you know that is okay. I do not want you to say it, I want you to get it, just for the sake of recapitulation. So, after time tau, your I is, the steady state value is v by r. So, I s t times, where is it here, times this becomes minus 1 minus e to the power minus 1, this is comes to 0. So, in some books that is why it is given that the tau is the value after which the current reaches 0.63 times the final value, and this concept carries on to the capacitive circuits and all that. How would it translate to mechanical systems? This is something that is generally dealt with in relationship to the electrical systems. How would you translate this to the mechanical systems? A mechanical RL circuit means what? Mass and a damper. So, a system which is something like this, a mass and then it is being acted on by a force that starts acting at a certain time. So, it will keep moving. Can you see that? It will keep moving, but the speed will slowly increase and then will reach a certain value, and then all that whatever you have learnt will be applicable in the same way. In case of the RC network, how will you do that? In case of the RC network, again writing the equation first, it will be V is equal to R I plus, how much is the current here? 1 by C integral I dt. How much is the voltage here? So, you just differentiate it, you get 0 is equal to r di dt plus I by c. Okay. So, the equation is di dt is equal to minus 1 by r c times I. Okay. Now, in the same way, if you obtain the equation, obtain the solution, it will be I of t is equal to some initial condition. Remember that it has already come in a x dot is equal to a x form without the additional term. Why? Because we have obtained in terms of I. If you obtain in terms of the voltage, it will not come in that form, whatever it is. So, this is convenient. The solution is I naught e to the power minus 1 by R c t. Okay. What is I naught? Initial current. If there is no charge initially, then the voltage here is 0. So, the whole current passes through this V by R. So, I naught is equal to V by R. So, this is equal to V by R e to the power minus 1 by R c t. In that case, what will be the waveform of this? It will be what will be the waveform of this? Obviously, it will be starting from. So, this is I, this is time, this is V by R. So, exponential decay starting from V by R. What will be the waveform of say V R? Yes, V R will be proportional, V C opposite, increasing. So, it will be, let's draw the V C. V C will be, will ultimately convert onto what value? V C kitna, how V, it will convert onto V. So, this is the current axis. So, we cannot draw it exactly on this, it will be in a different graph t. This is V C, here is V. So, it will be fine, this is V C. The current graph is like this, V R graph is similar, V C graph is like this, and in all that, will the time constant be different in these graphs or will be the same? Yes, that is the point. So, a circuit will have the same time constant for all the different variables in question. And in this case, what is the time constant? R c, because the waveform is like this, tau is minus t by tau, tau is R c. Okay, good. So, you have learned how to solve this. Now, how do you then apply this concept to RLC circuit? You have got a switch R L C how will you apply this? I would calling it V. Okay. So, again write down the equation. V is equal to R I plus L d I dt plus 1 by C integral I dt is equal to 0. Sorry, V is equal to, sorry. This integral is problematic. So, let us differentiate it through. You have 0 is equal to R d I dt plus L d2 I dt2 plus I by C. Okay. So, you have L d2I dt2 plus R di dt plus 1 by C I is equal to 0. How will you obtain the solution? Of this, yeah, this is homogeneous, this is right hand side is 0, there is no forcing function appearing in this equation, it will appear, but when you write it in form of I, it does not appear, that is an advantage. Good. So, we do not have to change the coordinate, we would have to change the coordinate if we wrote the equation in terms of something where the equilibrium point is not at origin, but in this case it is. Good. How do you solve it? You already know that you will have to write it in the form d2I dt2 plus twice zeta omega n di dt plus omega n square I is equal to 0. The moment you write in this form, then these values will tell how the solution is. Good. So, you write down what will be omega n square. Yes, L will have to be divided through, because this has to be divided of this L. So, it is omega n is equal to 1 by root LC, fine. If omega n is this and twice zeta omega n is R by L, then what is zeta? R by 2 root over C by L. See, check R by 2, sorry. So, this is how we are obtaining this, and then we do not really need to solve it, because we already know the solution. We simply decide in terms of these values, and you can easily see that the natural frequency of oscillation in the absence of zeta will depend on root over LC, and the zeta will be dependent on R, L and C, all of them, but you can see that zeta will increase for increasing R and increasing C by L ratio. Okay. So, if you have these parameters and say you have this as a rheostat, and if you smoothly increase it from a small value to a large value, then what will you see? No, initially it will be under damped, it will be oscillatory solution, because the eigenvalues will be complex conjugate, and as you change it, it will slowly become firstly a critically damped situation when this is equal to exactly 1, and then it will become over damped, fine. When it is become over damped, you can still write down the time constant, clear. You can at that time write down the time constant, because it will then be a exponential solution, and write down. What will be the critical value of R at which the changeover will take place? R critical, substitute this as 1 and then obtain it. Okay. So, when it is over damped, what at that time will be the time constant? Go back to the pages where we did this, and you will be able to obtain it. Anyway, I will leave it for you to do. But remember, most of you often visualize the time constant only in relationship to RC network or a RL network, but when it is a RLC system, then also there will be a time constant depending on when it is overtime system, and that also you should obtain, get it. What is the equivalent mechanical system in this case? Rlc series circuit. Yes, mass spring damper, we have already done that. Mass that is it with a forcing. All right, it will have the same bond graph. If you obtain the bond graph, it is 1 SE, then I C R, a series circuit. Fine. So, its behavior, this kind of a system's behavior will also be determined by the same kind of dynamics, and depending on the value of the damping, it will either be underdamped or overdamped. Not only on the value of the damping, remember it also depends on this term. So, if you keep the R constant and vary this, that means you suppose slowly increase this spring constant, then also it will exhibit the same kind of behavior. Clear? Okay. Yes, I knew that you have done the time constant business earlier, but nevertheless it was necessary to place it in a general format. Good. Now, suppose you have got a square wave as the input voltage. Then what happens? Then remember, if it is a RLC circuit, the state space is 2 dimensional, right. The state space is 2 dimensional with what are the 2 state variables? The current through the inductor and the voltage across the capacitor. Fine. And then as you obtain the equations, okay, one thing I forgot to deal with. Suppose you have a oscillatory solution or a overdamped solution, whatever it is, this is a solution of the I variable. What about the voltages, say VL or VC? What is VL? LDIDT. So, you have to differentiate it, and then this will give this value. Then can you draw, supposing this gives a overdamped response, can you draw all these variables? Before I go into this, I will have to just clarify the concept there. Can you draw all the variables? Overdamped. So, what happens to the current here? Current starts with 0. Its steady state value is 0, because the capacitor in steady state it blocks, in starting condition this blocks. Therefore, the current starts with 0 and ends with 0. So, when we are talking about the time constant, you didn't notice this. I was trying to get you at that. Yes. So, it will be essentially a rise and then a decay. It will be rise and a decay I with t. What will happen to the voltages? Voltage across the R will be obviously proportional to the current. What will happen to the voltage across the L? You are talking about the voltage across the L. It will start from 0. Okay. uh, starts from where? Initially the current is 0, therefore the voltage across this is 0. The capacitor voltage is 0 because there is no charge in it. So, it will start with V. So, di dt L di dt is V. So, di dt is V by L. So, di dt initially starts from some value, which means I was somewhat surprised. Didn't you protest this? Didn't you protest this? The slope should not be 0 when it starts. It should start like this, right? Is that right? So, it should start like that at some slope, which is V by L, and then it will go like this. Yes, now logically obtain the other waveforms. Logically obtain the other waveforms. Initially the current slope di dt, you have decided that it will start from some value V by L, or the voltage across this is V, and then it goes to so 0. Ultimately, when it becomes steady state, the current is 0, slope has to be 0, right? If the current is 0, the slope has to be 0. So, there also the slope is 0, the current is 0, so that means it reaches like this, but from the positive side or the negative side, does it go negative? Does it go negative? Okay, okay, okay. Now, slowly you are trying to organize your thought, organize it, draw it and submit it to me. You have done RLC circuits for how long, I do not know. Still I knew that this would give you trouble. Good. Okay, let that be an assignment. Draw it correctly and then submit it to me. Now, we were talking about what happens if you have the RLC circuit and you have, or say maybe RL circuit simply, RC circuit whatever, and you have the forcing function as a square wave. If it is a RC circuit, then what will be the waveform be? The capacitor tries to charge to the applied voltage, but then the applied voltage changes to a negative value, it tries to follow it, again it tries to rise, it tries to follow. Okay. How did I obtain without solving it? Simply by understanding that all the time it is trying to reach the equilibrium point, and it has to do so exponentially. So, all these will be exponential things, there is no other way for it to do. If it is a RL circuit, then what happens? Then the current tries to reach and the current waveform will be similar. Okay. So, let us talk about more important and visually beautiful thing, that what happens if it is a RLC circuit. In a RLC circuit, if you apply a voltage like this, where is the RLC circuit equation? It was here. RLC circuit equation is this. So, the current's equilibrium point is at I is equal to 0. What about the voltage is equilibrium point? It is not. And the state variables are this, and the current is one state variable and Vc is another state variable. So, what is the equation for Vc? Equivalent equation for Vc, or in other words, the way we did it was, if you have this equation, then you can write it in equivalent first order form, in which I will be one variable and di dt integral IDT Vc will be another state variable. So, you have two state variables, out of which one will be the Vc, the other will be the I, and therefore, Vc we can easily see, if you consider Vc, what will be the equilibrium point for Vc? V. So, it is different. So, if it goes like this from plus V to minus V, in the Vc there will be one equilibrium point here and another equilibrium point here, you can see, with I value 0, clear. So, once it will try to reach this particular equilibrium point, when it is here, again before it reaches, actually, because it actually reaches after infinite time, before it reaches, the equilibrium point jumps to this value, this value, and then it tries to reach here. So, what will be the orbit like? First it will try to reach like this, say it is oscillatory solution, it will reach like this, and then suddenly it will go there and it will try to reach like this, again it will go there, it will try to reach like this, again it will go there, try to reach like that. Okay. Does it stand to reason? So, in the state space you will find that the equilibrium point is shifting and this fellow is trying to follow it, but before it can reach, it jumps back. So, it comes back and it goes around it. If it is a non oscillatory solution, it will go straight like this, it will try to go straight and then it will try to come here, it will try to go straight, it will try to come here, like that. If it is oscillatory solution, it will be going around it for some time, but before it reaches, it will have to jump back to the other. In time domain, what will be the behavior like? In time domain, how will it look? Suppose your suppose I am drawing the waveform for Vc, then it will try to reach Vc, comes very close and then it jumps, then it jumps. Have you seen this waveform in your experiment on the CRO, on the RLC circuit? Yes, you have done that, you have seen that, right. This could be either like this, or it could be it could also be like this. Like that. This will happen in case of non oscillatory solution and this will happen in case of oscillatory solution. See, all these are coming in place the moment we look at it from the point of view of without doing a blind solution of the differential equation. What are we doing? We understand that if the equilibrium point has shifted, the way we showed a different way of solving the equation, we are actually conceptually doing that way. It is approaching that and then the equilibrium point is moving, and now without even solving the differential equation I can talk about it. Under which this will happen, under which this will happen, that depends on the zeta and omega n. Clear? Fine. So, this is done. What other type of forcing function can you visualize? We have done a single step function, we have done a square wave function. What else could be? Sinusoid. Okay, let us take the sinusoidal forcing function. Let us take the sinusoidal forcing function. Now, here in this case, notice you have the equation in the written in the same way. If it is a okay, first let us do with RL circuit, RC circuit, and then go ahead to RLC circuit, otherwise it will be difficult. But nevertheless, what is happening is that the sinusoidal forcing function will cause the equilibrium point to move continuously in the state space, and your actual state, if the system is stable, then will try to follow it. Okay, it will never reach, but it will try to follow it around. Okay, clear? And so it is not difficult to see that if it has a certain type of waveform, the following thing will also have a similar type of waveform, right? It does stand to reason. If I have got something moving and the other fellow is trying to follow it close in heels, they will have move in the same way more or less, right, with some difference. It will not be exactly the same, but we will have the same type of waveform. So, if the forcing function is a sinusoid, logically we expect the solution also to be a sinusoid, right. Okay, so let us do it for today, at least with the time that we have remaining. Let us do it for a RC circuit. We have a switch and then a RC network. Write down the equation. In this case, V of t is some maximum voltage sin omega t. That is how we have applied the voltage. So, the equation is this voltage is V m sin omega t is equal to R I plus 1 by C integral I dt, right. This is uncomfortable, so let us differentiate. Let us write this in the left hand side. You have R di dt plus I by C is equal to V m cos omega t. So, in order to write this without this r, we divide both sides by r. You have di dt is equal to or plus 1 by R C I is equal to did I write? Yeah, omega will come here. Yes, omega will come here. You are differentiating. This is r in the denominator. So, omega V m by r cos omega t. So, this is the equation. The question is, what will be the solution? The logic that I proposed was that in this case the equilibrium point moves sinusoidally, and naturally the current will also follow it, and you can expect a sinusoidal function as the solution. What is the general form of a sinusoidal function? A sin omega t plus b cos omega t. So, a possible solution is, we will check whether it could be a possible solution, is I is, I will write it as I p is equal to A cos omega t plus b sin omega t. Why did I say that this is a general form of a sinusoid? Because cos omega t has a 0 at pi, no, pi by 2, 3 pi by 2 and all that. Sin omega t has a 0 at 0, pi, 2 pi and all that. So, they are exactly 90 degree out of phase. Their addition, depending on the values of a and b, can yield any possible sinusoid in between. That is why this is called the general form of the sinusoid.
So, going with the reasoning that if the forcing function is a sinusoid, the solution has to follow it. That is one thing, but so will it follow it fast enough so that we actually see a sinusoid?
No, it will be lagging behind that. So, there will be a phase. but if something is going like this and the another fellow is trying to follow it, it will follow the same kind of, but it is a roundabout logic. I am sort of hand waving to give that logic, but we will have to mathematically check if it can be really a solution. Okay. Yes, you are right. This hand waving logic is intuitively good, but after all we have to prove that it can be a solution. Clear?
And if you have an equilibrium point, then we have to give some time for the
his point is that if there is equilibrium point, we have to give some time for it to reach there. No, it will never reaches there. By the time it starts and by the time it goes, this fellow has already moved. So the equilibrium point is moving like that, and the solution point, the state in the state space, is following it, and while it follows, there is no time for it to reach, because the that fellow is already moved, right? It is moving all the time, so it never reaches. But what happens is that, have you ever seen the flight of bees? One bee flies like this, the other bee follows it, and then they move in the same way. Talking about waveforms, they will have the same waveform with some difference. We'll talk about those, but yes, this is a hand waving logic, and we'll have to prove it. So how to prove whether this can be a solution of this? Just differentiate and substitute it here, and if it can be obtained, it's fine, right? So let's do that. Let's do that. Differentiate this and substitute here. So d I p dt is minus a omega sin omega t plus b omega cos omega t. So I want it to be a solution of this equation, so we substitute it here. It is minus a omega sin omega t plus b omega cos omega t is this term, then plus 1 by R c times this, it is 1 by R c times, where is the solution? Yes, here. So 1 by R c times a cos omega t. So a by R c cos omega t plus b by R c sin omega t is equal to, so this I have done equal to omega v m by r cos omega t, omega v m by r cos omega t, fine. So I can see that this equation has sinusoidal terms, this and that, and cosinusoidal terms here. Under what condition will the left hand side and the right hand side become equal? Yes, the coefficient must equalize. So this coefficient plus this coefficient must equalize the right hand side coefficient of sin omega t, which is 0. So we can write minus a omega plus b by R c is equal to 0, and the coefficients of the cosinusoidal term, this it is b omega plus a by R c is equal to omega v m by r.
So, but how can we write it this way? Cos omega t and sin omega t are not two independent terms.
No. The point is that yes, they are independent terms, because they are 90 degree out of phase. They are 90 degree out of phase. They are independent terms. That is why you can write it this way. They will. This equation can be is possible only if this is true. In that sense, okay. Now we can see that from here we can, is a two equation, two unknowns a and b. We can extract the values of a and b, which will satisfy this. That means if you obtain the a and b from here and plug it in here, you will get an equation for IP which is a solution of this equation. Fine. which is a solution of this equation. So, from here just obtain the values of A and B, just obtain the values of A and B. They will turn out to be, just check, A is equal to omega c V m by 1 plus omega square r square c square, and B is equal to omega square r c square V m by 1 plus omega square r square c square. So, your solution is I p is this cos omega t, this sin omega t, that is it, fine. So, A cos omega t plus, okay, we will continue with this in the next class. Thank you.